Where's the announcement? Announcements. Syllabus, assignment. Midterm. Okay, download.
Shall we start? Basically, you are graduate student. I think you understand that, right? So usually prioritize your research. And actually, we have a faculty meeting every week. Not every week, every month. Okay. So I heard some faculty complain with me. Some of his students, her students, complain about the homework and midterms and whatever. And the student saying that he's trying the best to do all the work by him or herself. But other student that's use the AI to do the job, and the student feels it's unfair that everybody get high score. I mean, the AI has issues, indeed. I mean, it solve issues and create issues. And for me, the same thing. You cannot trust whatever AI ever said, okay? So I find very interesting phenomenon. I was trying to dump a question to Gemini. And I find that actually Gemini got improved significantly over the past few months. At the beginning, when I gave the question to Gemini, he's saying, give me some answer, and I told, okay, the answer is wrong. And then, oh, I'm sorry, so it's wrong. And then he trying best to fix the issue. But nowadays, I'm saying that, okay, the answer is wrong. You know what's the answer? No, it's right. Okay, the progress made in the last few months is that the AI start to learn how to make argument. In my opinion, it's more dangerous because it's more confidence. And then, probably, if you do not have a very clear mind, probably just trust the AI. There's a very interesting psychology phenomenon people were saying. I mean, I saw this video on YouTube. These are funny. Saying that there's a guy robbing the bank, and then with no cover on face, everything got exposed, and he was kind of robbing the bank, and then and then got caught up immediately. Okay, and the police officer asked, "Hey, why do I rob the bank? I mean, I need money." Okay, and then the guy got really confused. Why? How could you find me? The camera, nothing got covered. We can identify with no time. That's weird. When I came to the bank, I already, cover my face with the lemon juice. Why? Because you suppose that lemon juice can hide everything. And you know that how he learned that technique? Because you use lemon right on paper, whatever. You can hide the lemon and eventually some chemical bring it back. And he think that use the lemon can also hide the face. And he said, I even make some experiment and test that the effectiveness of it. And then police officer, how do you do that? You know, I take myself and I take a picture. I cannot find myself in the picture. And then the police asked me, okay, just show up. And eventually figure out he used the other side camera.
Oh my God.
But the thing is, that's the reason I'm saying that AI sometimes dangerous. Sometimes overconfidence only means you are not understand the principle of something at all. Okay? You can see this kind of curve. People very confident. One extreme know nothing. The other extreme know everything. But in the middle, people sometimes don't have that confidence. You can see that's the reason quite a lot of scientists are not very confident. They are very humble about discussion. They want to listen because they are not very confident about whether they are right or right or wrong. But if somebody can tell you 100% I'm right, either is really expert or knowing nothing about it. That's something I can probably Gemini right now is the other extreme. And this is how I design the midterm, okay? So let me give you some example. Go through it briefly and to give you a peaceful mind that as long as you do the job by yourself, I can identify. But if you do this job by AI, I can also figure it out very easily. You know what? The ChatGPT, the Gemini, or other kind of like the accessible model are all we call is the big language model, right? The big language model actually can build up the correlation between objects. For example, if we are talking about the law, if we are talking about thermodynamics, and it can automatically link to the first law, second law, third law, okay? And then if you talk second law, it's automatically linked to the entropy, okay? Because I mean, they know this correlation in the mathematical model. But it doesn't necessarily means the AI understand the principle of it. You know what I'm saying? They just give the reason and the result are totally different from the correlation, right? The two things may have the correlation to each other. They have some connection to each other, but not necessarily means A causes B or B is the reason of A, right? But probably that's just two different things. But AI cannot do the job so far. And based on that principle, I can design this one for you. Let me show you how did I fool the AI, okay? Look at this one. We are talking we already mentioned about this kind of the question in the class, right? The osmosis process. So when we talk about class, I talk about something like this. So why it happened? Because I told you that one side of this tank, one side of the U-shaped pipe is filled with water and salt, right? And the other is only water. And in the class, I mentioned that probably we have 95% of the water. Then we just treat water and salt as ideal gas. This is really ridiculous assumption, right? But it can help us to simplify the model, right? Then we simply do not worry too much about the structure of water and salt and more. This is one molecule, this is another molecule, right? We know that's 95%, this is 100%. And then we know the partial pressure of water here is only 0.95 P. And for here, the partial pressure of water here is we don't call it P1, P left. This one is P right, right? And then what we need to do is, since this water, okay, they should share the same pressure, right? They're equal to each other, right? And then and in the pressure, we already know this is 1 atmosphere, right? And we know the pressure on this side is what? Is 1 divided by 0.95. That's it. You get the answer. Okay, the answer is only do this one, okay? That's how much pressure you need to give this one to make the water to go to that one. Simple, right? If you know that we use the ideal gas assumption, it's very simple. I mean, if you know that one, you can calculate this one with them. Did that spend half minute to do that job? No, right? But I can clearly say that I can clearly see some people use the AI to do the job. Let me show you, okay? So I have one, see the screen? I have one statement here. Okay, treat water and salt as ideal gas approximately. You know that this indicates that we do not need to consider this one. We don't need to consider the structure or ionization of salt and anymore, right? Let's go to the Gemini. Let me show you, okay, to see whether it's right or wrong. You see that I give it all the stuff right here, right? See, it doesn't understand why we have the ideal gas. It still considers sodium ion and chlorine ion, right? And it's also bringing something not related to what we're talking about, right? See that? And the sea salt, RT, we do not consider this one. We do not even consider this at all. So if I see that you solve this problem with this way, I can identify that use AI to do the job. You got 0 point. Okay, for that question. Understand something? Okay. As long as I saw that you consider the ionization, I know that you use AI to do the job. The other question. We learn the Carnot cycle deliver the highest efficiency. Briefly describe the picture. If we can build an engine with this efficiency, that means the highest efficiency, and equip your cars for traveling. So I designed this question. I know I briefly checked your homework on the midterm. People give me different answers. For example, my student tell me that if you build up this one, because the Carnot cycle is a thermal equilibrium process, then we need to make sure every step of thermal equalize, and this one can be extremely slow. Okay, that's acceptable. That is acceptable. Okay, that's what I'm saying. Okay, if you want to build up the reversible process, everything will be very, very slow. That's fine. But when I designed this question, my idea is like this. So we are talking about this one. If this one has a highest efficiency, then the entropy of the system doesn't change, right? Correct? The Carnot cycle doesn't bring any change to the entropy, correct? After the cycle, nothing changed, right? And then this is the reversal engine. Understand something? This is the reversal engine. So what does the reversal mean? Reversal means that this process is not spontaneous process. Right? Think about you equip a car with this engine. The engine cannot run on itself, right? You put the gasoline, it doesn't run because it's not a spontaneous process, right? That means if you build this engine, put the car simply doesn't run. Correct? Is that simple? That's very simple. Okay, let me see what's the Gemini doing the job. You see that? It's always talk about the efficiency, the mileage waste, whatever. Okay? You know what I'm saying? That is always assume this is impossible to achieve, and explain to you why it's impossible to achieve. Because you have large amount of data online, teaching materials, and practice to ask the student why they cannot enter, why this kind of the highest cannot be achieved. That's the data set, right? But if we break that data set, okay, we talk something outside the database. What if this one happens? The AI cannot give you the result. You know what I'm saying? But we can give the result. That's a totally different. Okay. So if I see the student talking about, okay, there's a friction, the turbo engine, and the combustion chamber, we have the thermal waste, whatever, you got 0 point.
Why, Professor?
Huh?
Because we have been studying about this Carnot engine from our 7th or 8th grade.
Yeah.
And we have been studying about eta equals to 1 minus T2 by T1.
Yeah.
So we can talk about that, right? It does not mean that we are using the AI. Because we
You can talk. I mean, I can tell. I can tell. You know what I'm saying? So the even you're talking about that is impossible to reach that one. That's okay. Okay. But you will not give me so much. I find the result from students. Okay. They talk about okay. There are so many frictions. For example, like turbine engine has the efficiency of that much, and the combustion chamber have the engine has the efficiency of that. How do you find this data? Right? You just copy paste the answer from AI, right? So but anyway, so I cannot guarantee that when I see this answer, I give you 0 point. It's totally fired, okay? But if you find that this is not unfair, come to my office and talk. We can solve this problem individually, okay? It's very simple, okay? I have a way to tell whether you use the AI to generate the answer or this answer just from yourself. I have a way to tell, okay? I mean, this is basically we just copy, okay? I already mentioned this in the class, okay? I think we already proved that in the class. And the other funny thing. Okay, so talk about that one. Talk about this one, okay? But sometimes I find some answer you are overthinking. You guys overthinking. For that one, for this one. So I ask you to calculate the enthalpy change, right? Let me see what's the AI do the job. I think the AI also
think about the actual case. The other thing is that I can try to fool the AI is something like this. So we give a very accurate, very specific example, right? Nickel and iron alloy, right? So if we drop this kind of knowledge to the AI, they start to dig the database and try to find the actual experimental value of it, right? But we don't need to do that, okay? So let me try to copy paste this one to the AI to see what's going on.
It's not possible to paste that image for sure.
You can put the image in on. I tried several times to put the image on as well. They simply ignore it. You can put the image, upload the image to there. You see, if you're talking about the AI, of course, we introduced this one in the class, indeed. But I do not think you can know this number from the figure, right? It's really hard. And you can see that it's always tell you, okay, you have this number, and then I'll also tell you the number is the minus 85, whatever, right? This is what the AI tells you. But I think when I designed that one, I told you, do not use any kind of data. Just use the data provided in this paperwork, right?
What about the book?
Yeah, the textbook has it.
The textbook, if the textbook has it,
Has
yeah.
a temperature, which is essential.
Huh?
Has a temperature of
Yeah,
this
it's,
round.
in the textbook it's 1600, but I mean.
Okay, if you use a
could
1600,
you
that's
like
fine.
Use a room temperature
Yeah.
as well.
Yeah, I mean, show me, okay? I mean, anyway, so but let me tell you how we solve this problem. Okay, easiest way, okay, easiest way. That's the reason sometimes my student told me that 3 hours is not enough, but I told you how we can do this job very easily. I believe there must be some chaos, okay? But feel free to come to my office, complain with me, okay? For that one, okay? So this is the figure. We know that this one is this is the ideal solution, right? But the actual case is something like this. Correct? Something like this. So remember, we will talk about the change of the entropy, or change of the Gibbs free energy is equals to what? Equals to the, I forgot the equation. Is the, what's the equation? By the way, it's not, it's fine. So it's the, for example, if the entire mixture is 1 molar, okay? Then it's XA RT ln AA plus XB RT ln B. Okay, this is affinity, right? And this is our curve, right? Yeah, this is affinity. Correct, everybody? And remember, if we assume this one is the regular mixture, then the TDS is simply XA RT ln XA and plus XB. Correct, everybody? We just use that one to remember that one, that's it. Okay? And you can see that if we're talking about, we have the nickel, what's that? We have the 0.02 more of nickel, then the nickel is here, right? The nickel is here. Correct, everybody? It's here. Oh no. It's
Sorry,
Yeah, shouldn't
It's
the,
here.
Yeah.
yeah,
Here.
should,
It's here, right?
Yeah.
It's here. It's here. Okay? Anyway, but you can see here, simply doesn't change.
That's
right?
a screen, Professor.
What? I know it's a screen. This is the erase. Okay. I saw somebody just use a marker to draw something on the projection screen. That's a disaster. Anyway, so you see here, right? And then this one doesn't change, right? So that means what? That means you only need to consider this term, right? Then the change of the entropy is simply equals to XA RT ln AA X. That's it. Simple, right? And what's the percentage? This one is what? Is 0.02, right? And reading from here, you just estimate, okay? It's not very accurate, okay?
found something in the textbook to where it's supposed to be negative, so.
It's negative, of course, because the affinity, you see that one is lower than this one, right? So this value
is lower than XA. So this total is lower than 1, so it's not good. That's simple. Do you think it will cost you 5 minutes to finish your job?
I've never seen it before, so it took longer.
Anyway, I do not mind that you make an answer very complicated, overthinking. That's totally fine. Okay, as long as you do it yourself, I'm okay with it. Okay, that's the reason I told with some student come to my office and complain. Oh, how do you know? I told them, if you make a mistake, it's fine. I want to answer the questions. As long as you try your best to solve the problem by yourself, I guarantee you can get a score no lower than A minus. But if I identify that you use AI, the highest score probably B. Okay? But on the other hand, I told you that for the homework, yes, you can use AI to help you do the homework. But for the examinations, no. Okay. Honestly speaking, I have not finished grading the. Actually, I'm not beginning yet. I even have not finished the homework to grading yet.
One was also not done for me.
Huh?
Homework 1 is not done for me as well.
Because you did not submit. I'm sorry. I will check. Okay. I will check. I know that several persons have not given them yet.
How many homeworks are left?
One more, right?
We're supposed to have 2 more, but 1 more is fine. Because we only have 1 month for the midterm, right? For the final, right? So probably I give you 1 more exam. 1 more homework.
So professor, final will be in December or November?
I try to make it in November.
Oh,
Okay.
isn't it like determined by the university? Like,
But that's for
One thing is,
oh,
you're not undergraduate anymore, you're a graduate student, okay? If I want, I can simply ask you to give me a presentation for that one. There's no there's no requirement from university level that what's the form of the final exam looks like. But for undergraduate, yes, there is.
in
Okay?
the other structures, probably we have like a fixed slot, which is like in the evening and not ideal.
Let's forget about that. I mean, probably, it depends. It depends. I have not finished grading the midterm yet. It depends on how many people I suspect will use AI. If a lot, in class. Okay? If not, take home. Okay? What's your question?
Is the final comprehensive
What do you mean by comprehensive?
for everything from
Oh, no. Just the one after the midterm. Okay, we don't want to repeat the same thing again. Yeah, I think I don't have that much question. Oh, wait, think about it. What design question? I need to think about what's the AI's response. Okay, make the job very challenging. Okay, anyway, so the, okay, so what's the, we talked about last time? We talked about phase diagram, right? I think that the, we may have no time to finish all the textbook. And I don't think it's necessary for us to finish the entire textbook either. Let me try to lock it. So the, let's see how much we can cover. Okay? How much we can cover. But I'm very surprised that this semester there's no hurricane. That means we need to finish all the semester. That is.
Professor, what if it happens during the final?
And you get an A.
It's not the season, okay? I mean, if it indeed happened during the final, that means the climate change is real.
Right?
Yeah.
Anyway, so the today we're going to talk about the reaction of the gases. Okay? The first topic we talk about is the equilibrium. Equilibrium of the chemical reaction. So the before this class, we all talk about the mixture, alloy, or whatever. Basically we use the first part of the class. We talk about fundamental principles and relationship in thermodynamics. And when we move on to the phase diagram, we start to consider the phase transformation and change interaction between different kind of the atoms. Okay? So, and you can see that from that part we use because most of this kind of the mixing or alloying process happen at a constant temperature and constant pressure. So we use the Gibbs free energy for description. And the equilibrium state give us the lowest Gibbs free energy, right? And we also talk about the regular, non-regular solution, all right? And in that kind of case, we start to think about the change of the enthalpy, right? Because the configuration of a chemical bond start to change, right? And basically, we can move forward and use a simple principle. We can start to analyze the chemical reactions. So chemical reaction is a very extreme case that we need to consider reconfiguration of the atoms, right? So some parts still working, some part doesn't work anymore. So for example, when we calculate the entropy, so for the mixture for the Loi, we just assume that the atom is randomly distributed in the system, right? We can calculate the configuration entropy. But for chemical reaction, it's a different story, right? Because they have their own order, right? They build up new orders. So the similar thing is when we're trying to understand the chemical reaction, we still use the Gibbs free energy because the reaction happens and most of the reaction, we control them at a constant temperature and the pressure, right? So because of that, we still can use the Gibbs free energy to analyze the reaction of the chemical reactions. Okay? So first of all, we talk about the reaction of gases because we use the ideal gas approximation to treat the change of the gas. Okay? So for this chapter, there are not too many interesting things. Okay, I just follow the textbook. Okay, so in the textbook, we just give us an example. Okay, we consider a reaction. Okay, it's A is a gas phase plus B in gas phase, and then we have the reaction in that way. The two motors of the C gas. Okay, this is a chemical reaction. So one example of this reaction can be something like this. So we have a hydrogen, we have the chlorine, and then we have the reaction, something like this, generally two molecules of the hydrogen chloride. Okay, and we can have some other reactions. Okay. But the hydrogen and the chlorine are both in gas phase. Okay. Let us consider this kind of the scenario. Okay. So if we mix 1 mole of A and 1 mole of B, so what will happen? So consider that this kind of reaction just follow the chemical ratio. Okay, if the 1 mole, if we have 1 molecule of A got consumed, then automatically we have one molecule of B got consumed, right? Because the chemical reaction is need to have a very strict chemical ratio between them. So if we mix A and B in the reaction tank, in the reactor, okay, then when we consume the following scenario, okay. In the container, okay, we have the container. Okay, we have the reaction happens here. Okay, we have A, we have B, and after the reaction, okay, during the reaction, we have Na left over in the tank. Then what is the quantity of B left in the tank? If we have Na left in the tank, how much B we have?
Same.
The same, right? Then how much C we have?
1 minus Na, 1 minus N.
1 minus Na and times 2. Right? Because if we consume 1 molar of A, we get 2 molar of C.
Yeah.
Right? Okay. So then, in this kind of scenario, the Gibbs free energy, we call it G prime, okay? Simply equals to Na mu A, okay? Plus Nb mu B plus Nc mu C, correct? mu A, mu B, mu C is the molar chemical potential, or molar Gibbs free energy, or chemical potential. Correct? Okay, so we can put number in. We have Na mu A plus Na mu B plus 2, 1 minus Na mu C. Correct, everybody? Right?
This is all before.
After the reaction, during the reaction.
During.
Before is something like this. A is, initial, okay? A 1 molar, and then B 1 molar.
It's in equilibrium, right? It's
Yeah. During the reaction, some A and B got consumed and generate C, right? Something like this. Okay. So the next step for us to do is to calculate the mu A, mu B, and mu C. Then we start to define. We introduce a concept, we call it the standard state, okay? Standard state. The standard state means what? Standard state, or standard condition. For our topic, for our discussion, the standard state means 1 atmosphere, okay? The pressure of the system is 1 atmosphere, okay? Then we need to consider the mu A, mu B, mu C, okay? For the mu A, is simply equals to mu A non, okay? Plus RT ln PA. What that means? Let me explain that to you. Okay? Mu A non is the chemical potential of A under 1 atmosphere. Okay? And mu A is the current chemical potential. You know what I'm saying? And the temperature the same. They have the same temperature. Okay? They have the same temperature. Temperature the same. Okay? But why it change? Why it change? Because when A got consumed, the partial pressure of A decreased. Right? That's the reason the chemical potential also changes. Okay? Any questions? Any questions? Actually, more precisely, this one should equals to, we have another term, okay? Okay? But we already assume this is 1 atmosphere, okay? If we just use 1 here, this one simply equals 0, right? So we can ignore this term. That's the reason we call it the standard state. For the standard state, this is 1 atmosphere, this is 1, okay? Ignore the unit. This is the 1, then we don't consider. It's 0. It's just like it give us a reference point. Okay? But after we set this reference point, we doesn't change anymore. We don't change it anymore. Okay? Is that okay? Okay. And you can see actually this one is negative because the partial pressure is lower than 1 atmosphere. So this value is lower than 1, this one is negative. Then the chemical potential of A in the current after reaction is lower than the initial state. Okay. And for mu B, the same thing. And mu C, the same thing. So PA, PB, and PC are the partial pressure inside the mixture. Okay, after the reaction.
mu naught C means what?
Huh?
Suppose mu naught A means initial, right?
Means the initial or the chemical potential of the A gas under 1 atmosphere pressure. Okay, under the standard condition. Okay. Other points? That make sense?
But C comes later here. That's why I was asking. C was generated later, right?
What?
C.
C is generated, yes. It's generated, but we still know the chemical potential, right? Think about it. Doesn't matter. So that's, moving. Then we can put, let me see, can we make the job easier? Let's put this one into that equation to see what's going on. are doing? Welcome, have a seat. Okay. And of course, this one change to mu A. And this one change to mu A. And this one change to 2, 1 minus NA plus.
So the small p is the partial pressure, right?
Hmm?
Small p is the partial pressure.
Is a partial pressure. Is a partial pressure inside the reaction tank. Inside the reaction tank. Make sense? And also we know that since A and B, right now we use the ideal gas approximation, okay? Since A and B, they always have the equal amount, right? They always have the equal amount. If we treat both A and B as ideal gas, then the PA simply equals to PB. Correct, everybody? And then we can replace this one with PA. Okay? And what about the PC? PC, I mean, the PC is what? PC, let me, give me that. So for this process, we do not need, let me see what some other assumption we're using.
Total pressure minus partial
Yeah,
pressure.
that's the, what I'm going to do. Yeah. Well, might be something. Oh. Okay. So assume that before and after reaction, the total number of the atom doesn't change. Correct, everybody? The total number of atoms doesn't change. Right?
Doesn't change.
And the pressure shouldn't change, right? The pressure is the same. Then, we can calculate the PA, PB, and PC. PA, PB, and PC, individually, okay? So, actually, we don't need very too much about whether they change or not. So, initially, we have the total pressure P, okay? We just use the 1 atmosphere as the reaction condition, okay? And after that, it's still P doesn't change, because number of molecules doesn't change, right? And then and inside the P, we have what? We have Na molecules of A, right? Na molecules of A and Na molecules of B and 2 minus 1 Na. Okay, we just separate them according to the molar ratio, right? So that means in total we have 2 molar of gas, right? In total we have 2 molar of gas, right? And then it's the P divided by 2 molar of gas, and then times the Na. Okay, this is the partial pressure of PA. Correct, everybody?
That's the total pressure.
Huh?
That P
P is the total pressure. It's 1 atmosphere. Okay? And then for PB, the same thing, right? Na and the P. And PC is the P divided by 2 times this value, and 2 times 1 minus Na. Okay? And then this one equals to 1 minus Na times P.
Write 2 PA.
Hmm?
Directly you could write 2 PA because the mole is double than A.
Yeah, is that right?
The molar ratio of C is double than
Yeah.
A.
Yeah.
So we can write partial pressure will be double just.
Yeah. Something like that. Not double. Not double A.
Double of the A.
No, not double the A. A got consumed.
Oh.
C got increase. It's not the, they don't follow this kind of linear. It's one decrease and one increase. Okay, so it's the minus. Okay,
Yeah.
sum together. This is half an A, half an A. This is one minus, and then put them together. The total number is still P, right? So we can put this one back to the equation. And the equation become very complicated, I know, but don't worry about this kind of very complicated expression. It's nothing very complicated, actually. Just we need some patience. I suggest that you still follow what I'm writing on the whiteboard, because when I prepare the class, I'm trying to see what the textbook is saying. I think they missed some steps. Okay, so probably we got very confused about what it's saying in the textbook. I was very confused, probably better than me.
Can you please repeat that once? Y divided by 2.
Go back and check the video. After class, I will. Okay. You know what's the reason? Because if I go back to I forgot what I'm writing here. But we should admit sometimes the human being doesn't as good as the AI. You see, I forgot where I'm.
Sorry.
Okay, so we
Should
combine
change
these two
the
terms.
next line.
We have this term and this term are same, right? This term and this term the same. So we just add a 2 here. Okay, we just add 2 here. And remove this term. Okay, we just put that that one there. Yeah, that's it. And then I try right here. This one equals to NA. What happened? What happened?
No, I'm writing it's gone.
What's that?
We were writing it and then.
No, this one, this term and this term same. I just add a 2 here.
Okay.
I just move this term to here, add a 2. Huh?
Whenever you were changing the partial A in the line before,
Uh-huh.
like you went from partial B to partial A, what was the reason why you did that again?
Because A and B, they have the same molar amount, so the partial pressure is the same.
Okay.
Okay. Da, 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 da. Right. So far, so good.
What's the goal?
No, you don't want to run an exam. What's the goal?
Yeah.
Show some knowledge. I show some knowledge, I get my salary. And you got the knowledge, you pay. Anyway. May I read this part?
Yes.
So is there any particular reason why you write G prime?
Why I use such J prime? J prime just means that it's not the initial state.
Change.
I will explain immediately, okay, why we use the J prime. But we want to add a prime there. Okay? But one thing is that this is not a derivative, okay? Not derivative. It's just a prime, not derivative. Okay. This is the G prime. Okay? What is the initial G? That means before the chemical reaction. It's just 1 molar
Of Na.
Na and
B.
1 molar
B.
of B, right? Uh, 1 molar of the Na. What is not none, okay? It's not none. But we can call this one. It's not the one. We call it prime. This one we call it G. We just call it G. Okay, we call it the G initial. Okay, G initial. And this one G initial. Okay. It's just something like this. Correct? Why I'm writing it that way? Because even before the reaction, they still mixed. They all mixed. Correct, everybody? Even they have no reaction, the entropy changes. Right? Now we need to consider the entropy change. Okay? And that's the reason I have a prime there. Okay? Just distinguish. But you can also, it's fine. It's up to you. You can also write a GF. Okay? It's the final. I use prime, just follow textbook. Okay? But anyway, so let's analyze this one by one to see what's going on here, okay? So you can see that we have, basically I write this one in 2 lines on purpose. One thing is, this one is the change, basically it's about chemical potential, right? But you can see in this expression, all the chemical potential is the standard state, in the standard state. That means under 1 atmosphere. But we know that after reaction, the partial pressure is not atmosphere anymore, right? So what this term express? This term just tells us what is the energy change of the chemical bond, okay? Basically a change of the entropy, the change of the enthalpy, okay? Enthalpy change. And this part is a contribution of the enthalpy, okay? Basically this is the T delta S, okay? This one, okay? You know what I'm saying? So this one. You can see this is just like a mixture. I mean, the pressure changes and the mix the gases. This is entropy change. Let me try to explain, to give you a better explanation about why this one is entropy. Consider, before mixing, we have this one, 1 molar of mu A, 1 molar of mu B, right? And then, if we do not consider them, then this one equals to what? This one should equals to mu A non. That means the ideal condition, right? And then plus the RT ln partial A, original condition, right? Initial state, okay? Initial state. And plus mu B non plus RT, the partial pressure of B in the initial state. Correct, everybody? You got confused. Why got confused? You confused? This is the idea. This event told us, okay, we have the initial, before the reaction. Before the reaction, we have tank, right? Then we have A gas here, we have B gas here. This is the 1 atmosphere, this is the 1 atmosphere. But they are separate. They are separate. In this condition, the total Gibbs free energy the total Gibbs free energy, we call it Z naught, okay? Z naught is what? It's simply 1 molar of the mu A naught plus 1 molar of the mu A B. Correct? Mu B naught. This is before mixing, right? And then we mix them. Okay? Due to the mix, the entropy change, right? And then this equation becomes this equation, correct? This equation becomes this equation. And this term is caused by the mixing. The partial pressure drop, right? The partial pressure drop, right? This partial pressure drop to half. This partial pressure drop to half, right? Because of that, we can see this one become mu A1 plus RT ln half P, right? P, that's 1 atmosphere. Okay? And this one plus mu B naught from RT and ln another half. Okay? And then this one becomes mu A naught plus mu B naught plus 2 times RT ln half pressure. Correct, everybody? This is after mixing, before the reaction.
Oh, okay.
Right? After mixing, before the reaction. Correct, everybody?
Yes.
And then, let's see this equation. So that means the G prime is a function of NA, okay? Correct? Then let's try to see what about G prime NA equals to 1. So this is what?
You said it's before the reaction, right? But if you already mixed, it started spontaneously, right? This reaction.
We just assume.
Okay.
That's the difference from A and human being, okay? We just assume doesn't happen. Let's see what's going on, okay? See this one? I mean, the other thing is that the problem reaction needs some catalysis, right? Even without brain catalysis, it doesn't happen. Now look at this one. If I set NA1 equals to 1, then this equation should be the same to this one, right? Because NA1 equals 1 means that during the reaction, NA doesn't get consumed. It's just a mixing reaction doesn't happen. Correct? To see what's going on here. And though NA1 equals 1, then this one becomes what? Becomes mu A1, mu naught, mu AB, and then mu B naught minus 2 times mu C naught, and the minus 2 times mu C naught. Then we only have mu A naught plus mu B naught. Correct, everybody? And then this term, 2RT, ln half P. Correct? And this term is 0. You can see this equation the same. Correct, everybody? And you can see the difference. The difference is the contribution of the reaction, right? We start to bring some of this term. We start bringing the mu C. That means the chemical bond formation of mu C gives some contribution that change the total Gibbs free energy. And we also need to control the partial pressure of the C amount, right? That because this one also contributes to the entropy. Correct? So this is the chemical potential change. This is the chemical bond effect. This is the mixing or the entropy effect. So we have 2 effects. Got my points? We have 2 effects. And then let's understand this effect one by one, okay? One by one. So we know that the change of the entropy is what? Is the NA. Mu A, so mu B. Okay? And we can assume, I mean, we use this one as a reference point. We just assume, okay? We just assume, because we only need to consider the change of the entropy. We don't care about the absolute value. We only care about the change of the entropy, right? Then we can set this term equal to 0. We just artificially set these at 0 as a reference point. Just like the kinetic energy, just as potential energy, gravitational potential energy. We can use this one, define this one is the 0 energy point, or I can define the floor as a 0 energy reference point. Correct? It doesn't matter, we just set this one at 0, okay? Then this one becomes very simple. This one becomes the same thing. 1 minus NA. Okay? Got my points? And if we assume, follow the textbook, okay? If we just find a random number, okay? We just set this one to mu c equals to minus 55,000 joule, okay? What does that mean? That means the reaction release 500 joule if 1 molar of this reaction, A plus B. Okay. If we only have 1 molar of the reaction, we release 5,000 joule of the energy due to the chemical bond formation. Okay. And then you can see how the entropy change. May I just erase this part? Yes, okay. At the beginning, okay, this one is N, this one Na. Okay, this one is 1, this one is 0. That means on this end, there's no chemical reaction. And on this end, the reaction is fully complete, right? Remember, I mean, very careful, I define this part as 1, this part as 0. Just inconsistent with the textbook, okay? Okay, this is the before reaction, this means the reaction got fully complete, okay? And then you can see as the reaction going on, at the beginning, this point is just a mu A plus mu B. Okay, we know this point is 0. Correct, everybody? And after if the reaction is we fully finish the reaction, then this one is minus, is the 2 mu C naught. That means all chemical bond of A and B got broken, and we only have the chemicals C bound, right? And this is what? This is negative, and this point is negative 5,000 joule, okay? And it is a linear relationship, right? It's a linear, you can see that's a linear, right? So that means the entropy just have a linear line entropy. This is reasonable, right? Because it's only proportional to the number of the chemical bonds got broken and reformed, right? Reasonable. Correct, everybody?
This is del H over entropy.
Huh?
The down.
Yeah, it's down the entropy. Because we assume that the reaction released the heat, right? But of course, if you assume that reaction will absorb the heat, then they're going up.
So the entropy is decreasing?
We just artificially set it decreasing. We assume one. Okay, that's really, I mean.
But if del H is negative, it's spontaneous, right?
Not necessary. Let me tell you. For that one, yes. If we only consider the entropy or the chemical bond forming, yes, it's preferred from energy point of view. But we also need to consider this term, the entropy. Right? Because when we talk about thermodynamic process, we always need to consider the balance point. Energy or enthalpy and entropy. Right? Entropy tells us the system wants to become more chaotic want to be as chaotic as possible, right? And energy want as low as possible. That's the reason why I have negative sign in between. We need to consider both factors, okay? And this one only consider change of the enthalpy. Let's see what's going on with this term. Okay, so if you plot it out, basically, let me try to see. So if the Na, we know that if the Na equals to none, equals to 1 is already here. This is the equation, right? This is the expression here, right? And we also set this one as 0. Correct, everybody? And when you have this term, okay? And we know this term is the starting T times entropy, right? So with this, the pressure is 1 atmosphere, right? Pressure at 1, this one is half. So we just need to calculate the value of R2 RT ln 0.5, right? So this one is delta H. And then at the beginning, because it's lower than 0, right? So at the beginning, before the reaction, the entropy already is at this point, already negative, right? It's already negative. This point is 0, right? This one is already negative, right? Correct, everybody? And then, if the reaction got fully if after we fully finish the reaction, fully finish reaction, this term is 0, right? And all this becomes 0, right? And we talk about this one. This one is, this one is 2, this one is RT, and the ln P, correct? And we already assume that the reaction happened at 1 atmosphere. Right? We're going to talk about the pressure effect later, okay? But right now we just consider the, we call it standard condition. The final reaction is also 1 atmosphere, right? And then you can see the entropy eventually happening that way. Okay? And, oh, sorry. That is how the entropy change. Okay, this is 0 point. Correct? At the beginning, this one is a 2RT ln half. Okay? This is the entropy change due to the mixing between A and B. Correct? And as the reaction takes place, the entropy going down first, of course, because that means everything becomes negative, right? It's going down first. And after reaction fully finished, we end up with 0. That means everything becomes C. We only have one kind of atom. That means, of course, the under the standard condition, the entropy is 0, because we only have one type of atoms there. So the entropy is 0. Right? At the beginning, we have mixing, so it's slightly lower than 0. Right? Questions?
Yeah, sorry, Professor, I didn't pay attention to the P. Why did you change it to P? It was P by 2, right?
If the n equal to 0, this term equals 0, right? And this one is 2 RT ln 1 minus 0 P is P. It's from this term. It's from this term.
Okay.
Okay. And then if we combine these two effects together, we eventually have this curve. Correct? This curve is the change of the Gibbs free energy during the reaction. Have two contributions. One is the change of the enthalpy. The other is the change of the entropy times the T. Correct, everybody? And you can see, although as if we move this reaction forward, the entropy keep declining, but the entropy going down and going up. Correct? So then that means we cannot fully finish the reaction, right? Instead, the reaction will stop here, right? Which give us the lowest Gibbs free energy. Make sense?
Yeah.
Okay. Questions?
Why is the UA plus UB on top of that axis? Like,
This one?
How is it there?
Huh?
How is it there? Like, what's that axis?
With this axis?
Yeah.
This axis is just energy, okay? But for this one, I mean, because the entropy gives free energy and the T times S, they always follow the same unit. Right? We can plot them together. Okay, this one is just the minus TS, this entropy. Okay, and then this one is the delta minus TS. Okay, and then this one basically, this one is the Gibbs free energy. Okay, the Gibbs free energy. Right? So you can see how that gives free energy. I mean, basically what I'm saying is that you cannot use this line to determine when the reaction is going to stop. You cannot use that one either, right? But you should consider both factors. And this one gives you the lowest spots, gives you the condition when the reaction stop and then reach the equilibrium. Okay, let's see what's going on here in this specific case. Can you erase this part? The question is, we need to find the lowest point of G prime, right? We know that the G prime is a function of an A, correct? And in order to find the equilibrium spots, we just need to calculate this one. And this one equals 0. Then we find the equilibrium states, right? And start from very beginning, we know the G prime equals to what? Equals to NA mu A plus NB, NA mu B plus 1 minus NA mu C. Correct? From very beginning of the class, right? And then if you do the derivative from this one, we bring this one in, and got this one, we eventually get mu A plus mu B minus 2 mu C. 0. Okay? This condition gives us the equilibrium, right? Give us the equilibrium condition. Okay, so let me briefly discuss the physical meaning of it. Okay, let me briefly discuss the physical meaning of it. The meaning of what? Or in that word, this is in other words, mu A plus mu B equals to 2 times mu C. Correct? And we already mentioned this is chemical potential. Chemical potential basically you can call it the molar Gibbs free energy. That means if I add 1 molar of A into the system, how much Gibbs free energy going to change the system? Look at this equation. So from this reaction, if we consume 1 molar of A, we automatically consume 1 molar of B. And we generate 2 molars of C. Correct, everybody? And if we want to make sure that this kind of the chemical reaction reach the equilibrium state, we want to make sure that we want to in that condition. So if I remove some A and B to C, the total Gibbs free energy of the system doesn't change. Then it reaches the stable state, right? If it keep increasing, then it's moving backward. If it keep decreasing, it's moving forward, right? But when it's reached a spot that will randomly change the number of particles between A and B and to C, the total Gibbs free energy of the system it doesn't change. This is the stable state. Correct, everybody? Let's do that one. If we assume 1 molar B and assume 2 molar B, then the change of Gibbs free energy of the system is mu A plus mu B, right? And then we inject 2 molars of C, and then the energy, this 2 disappeared, and this 2 mu C increase, right? But you can see since mu A plus mu B equals to mu C, the total Gibbs free energy of the system change. Correct, everybody? Right? That's the reason. That's the physical meaning of this equation, and that's the reason we call this parameter the chemical potential. It tells us the potential or the trend of the direction of chemical reaction. You know what I'm saying? Think about it that way. So if the mu A plus mu B is larger than mu C, the reaction moves forward to this region until this one increased and this one decreased. Eventually, we reach this equilibrium state. And if this one is lower than that one, the chemical reaction will move forward to this direction. It's just like a potential energy. Okay, that's the reason we call this parameter chemical potential. Okay. And in the equilibrium, so basically for any kind of reaction, Na plus Mb equals to and equals to the probably Xc plus Yd. Just follow the same thing, okay? Is the mu A, N mu A plus M mu B equals to X mu C plus Y mu D. Okay, this equation gives the condition of the chemical equilibrium. Okay, got my points? Simple. Okay, anyway, so let's do more treatment on that one. Okay. And we know that this one is a chemical potential of A and B and C during the equilibrium, okay? And we also know what? We also know mu A equals to mu A non plus RT ln PA. Correct? We already introduced this equation. We already used that one, right? And the follow the same thing. We have mu B equals to mu B non plus RT. We can put this one into this equation. Then we have the mu A non plus mu B non minus 2 mu C non plus RT ln PA plus RT ln PB. minus. Correct? From this equation, we have this one, right? From this equation, we have this one. Okay, so they are equilibrium, right? Then they are equivalent. This one gives us the equilibrium condition. This one also gives us the equilibrium condition, right? Because we just replace the mu A with the mu A non plus RT, non-partial, right? And then from this one, we have mu A non plus mu A B minus mu C non equals to RT. Correct? And we define this parameter as the negative delta G non. Okay? So delta G non is what? Goes to 2 mu C minus mu A. Okay? This is the definition of delta G. This one we call it the standard change of Gibbs free energy. Okay? Is a standard change of Gibbs free energy. That means the not molar, the change in the standard chemical potential during the reaction. Okay? So basically, you do not consider what's the partial pressure before and after. You just need to know what is chemical potential of A before reaction under 1 atmosphere, and B before the reaction under 1 atmosphere, and C fully after the reaction under 1 atmosphere. Okay, and you have this kind of this one, the difference between the chemical potential. But you also need to add something here. Okay, is the we call it standard change of Gibbs free energy. Basically, it's consider both effects. Basically, the change from this spot to this spot. Okay? Change from this spot to this spot. But under the standard condition.
So this is a constant.
This is constant. You are touching the very important point. This one is constant. It's only defined by the material itself, independent of reaction condition. Right? Because we already defined condition is 1 atmosphere. So it becomes a standard, which become a constant. Okay? And then this one becomes what? This one is RT. Well, and then for this one, we define it as Kp. This one we call it the reaction constant. Okay? You will see that Kp simply equals to ln Kp. Simply equals to minus delta G non divided by RT. That's it. Okay. I think you learn this now, we call it reaction constant or chemical equilibrium constant in the high school or you know that one. But we never explain what's the reason for that, why we define in such a way. But right now you know. Okay? Question?
Yeah, why is delta G negative again?
Oh, because we define the delta G as the final divided by initial. But you can see this equation is the initial divided by final. That's the reason this is just definition. Okay? Because we always talk about the change of something. That means the final state compared with the initial state. Right? That's the reason we add a negative sign here. That's just a definition. Okay. Okay, so the key conclusion is that for this kind of specific reaction, the final state can be defined, we can find the final state by using this equation. Okay? For 1 molar of the reaction. Okay? For 1 molar of the reaction. Okay? And Kp is defined as
the partial pressure for this specific case. Okay, for this specific case. On my points? And if you know the change of Gibbs free energy in the standard condition, that means 1 atmosphere. And by adding the reaction temperature in, we can find the reaction constant. And from the reaction constant, we can find the partial pressure of the final product of each component. Okay? But of course, this one only works for this idea, for this case. If you have a reaction, for example, like MA plus NB equals to, for example, XC plus YD, then the reaction constant is something like this. Like the PC, X, PD, Y, and PAM, and PBN. Okay? That's all. Okay. This is the more generalized definition, okay? But for our specific case, something like this. Okay? And since at the beginning, I already told you what's the delta G, okay? This is what? The delta G is what? We mentioned that the delta G is negative 500 pure, okay? We already give the number in, right? So we can put this number in and calculate how much final product gonna generate from the reaction. Okay? Common point? All right, so the pressure effect. We know that one, this one is in the standard condition, right? 1 atmosphere, right? But I did not tell you that reaction must take place at 1 atmosphere, right? We can pressurize it. We can lower the pressure, right? This is not necessary. We always make this reaction happen under the ideal condition, under 1 atmosphere. So what if we change the pressure? We know that, look at it. This one, I did not tell you this part pressure in 1 atmosphere, right? Look at it. I only tell you this part pressure, right? But I did not tell you the final product has the pressure of 1 atmosphere, right? So that means what? That means this can't be writing that way. So this one is the ratio of B and the ratio of A and the ratio of B times, but for that one, of course, I mean, you can see this one is pressure squared, this one is pressure squared, right? And you can see this one become XC squared, XA, XB. So you can see that one, this one is independent of pressure, right? We know that the reaction constant is a constant, right? Because it only depends on temperature, right? But if you put the partial pressure in, you can see that if even we change the pressure, then that one doesn't change, right? That means the final product doesn't change, right? But what if the reaction looks like this? 1 mole of A react with 1 mole of B and generate 1 mole of C. Then we don't have the square here, right? Then we don't have this one, we don't have this one. This one become here. Then we have something that looks like this. Correct? We know this one is constant, right? That means when P, the pressure goes up, this one going down, this 1 over P going down, right? In order to keep that constant, the C needs to go up and A and B need to go down. That means if I pressurize the system, the reaction move forward, right? Correct? But in other way, if I if I release the pressure from system, the reaction moves to that direction, right? And the other case, the other example, if the 1 molar of B and 1 molar of C generates 3 molar of C, what will happen? Then we know that we have 3 here. We have 3 here, right? And the P move up, right? That means if I pressurize the system, the C needs to decrease. That means that I pressure the system, the reaction going to this direction, right? Basically, one way to remember the condition is that if the system, if the reaction introduce pressure to the system, you can see that 2 molar generates 3 molar is generate high pressure, right? Then if you release pressure, you give more space for the reaction, then the reaction can move forward, right? But if you press it, that means you're taking more space for the reaction, then the reaction will move backward. Okay? So basically that's something you need to remember. I think time's up, right? So for the next time, we're going to briefly talk about the temperature effect, okay? So this I briefly talk about next time, okay? And then we move on to the next chapter. Questions, comments? Okay.